I believe that every child is born curious. We make the coldest things that have ever been anywhere in the universe. And we do it in a completely counterintuitive way by shining light on stuff. Usually that's supposed to make things hot, and we make things cold, and colder than anything else has ever been. Temperature is about how fast things are moving. In fact, temperature is just a measure of the kinetic energy of motion of whatever makes up the substance of which you're measuring the temperature. The gas, the air in this room, because it's hot, the atoms and molecules are moving around really fast. If you were to cool down the air, the atoms and molecules would be moving more slowly. If they're moving more slowly, we can measure them better. I believe that every child is born curious. And I was, like all children, curious about everything. My parents gave me a microscope when I was about 5 years old, and I remember going around the house looking at everything. I think that sparked my curiosity and directed it towards science. And as time went on, I became more and more interested in science, and particularly in physics, because physics seemed so clean to me, that there were easily understood concepts from which you could figure out basic ideas. Just remember a few things and a little bit of math, and you could work it out. Well, today, the time that you get on your cell phone is ultimately coming from atomic clocks that use the technology that my group developed over the years for making atoms move more slowly. Because the atoms in these atomic clocks move more slowly, the atomic clocks themselves work better. And those atomic clocks are used to guide the atomic clocks in, for example, the satellite navigation system. It's going to have an effect in quantum information. The so-called second quantum revolution is based on doing things to atoms and molecules and sometimes superconducting circuits. And so we've enabled a new direction in physics by making atoms really, really cold. Often, when things just aren't working, a good strategy is to walk away, to do something different for a while, and somehow it seems that something happens in your brain while you're not consciously thinking about the problem that rearranges things so that when you come back to the problem, you see it in a different light. Another technique which is really useful is to explain your problem to a colleague who is not intimately familiar with the problem, but can understand your explanation. And sometimes simply the act of explaining it to someone else will reveal to yourself a new way of looking at the problem, or sometimes your colleague, looking at this problem from a completely different perspective, may come up with a suggestion that will be useful to you. 100 years since the development of quantum mechanics by people like Heisenberg, and a year later by people like Schrödinger, Dirac, if you had asked those people, what is quantum mechanics good for? They might have said, oh, well, we'll be able to explain the spectra of atoms and of molecules. We'll be able to understand their transition rates. None of those people would have been able to predict the transistor. The transistor has changed our lives in immeasurable ways, but no one would have been able to predict that at the time. We are at the beginning of what some people have called a second quantum revolution, where we're going to make use of the weirdest aspects of quantum mechanics: superposition and entanglement, the idea that things can be in two places at once, the idea that what affects this object here can have to do with something very far away over here with no obvious connection, and yet they are connected. That's what entanglement is about. The kinds of things that will bring about, quantum computing, for example, I think we can guess about the things that quantum computing might bring to us. People imagine better drug design, better design of materials, things that will be more energy efficient. We're always bad at predicting, and it's always difficult to know what something is good for until you've actually got it. And we're just the beginning of getting these new kinds of computers, these new kinds of quantum simulators, quantum communication. I don't think we are yet able to predict the most important things that are going to affect people's lives the way the transistor affected people's lives.